So let's start with the introduction of signal processing estimation theory. I will give some applications of estimation theory. So the first application is radar. The second application is sonar, speech, image, biomedicine, communications, control, seismology. So these are some of the applications, but there is a long list of applications of estimation theory. So, but we are going only to discuss the first three applications, that is radar, sonar, and speech. And we will discuss how estimation theory is going to help us in these three areas. So basically, the objective of the estimation theory is, so we start with the objective. That is, what is our objective? So the objective is to estimate the values of a group of parameters, unknown parameters. So we need to estimate some parameters whose values are unknown. So let's start with the radar first. So we will start with radar. So the objective in radar is to determine the position of the aircraft. That is, we need to determine the location of this aircraft. In other words, we need to find out what is the range, that is R. That is the distance between the transmitter or receiver antenna in the aircraft. So how do we do that? So the method is to transmit an electromagnetic pulse. So this pulse spreads out in all the directions, and then it hits the target, and then it gets reflected back to the receive antenna. So the delay in receiving the signal, which we denote as tau zero, is given as twice r over c. Twice r is the total distance traveled by the EM signal, that is the electromagnetic signal. So it travels a distance of r plus r, that is 2r, and c is the propagation of light. Okay, so if we can estimate tau zero, we can get an idea of what is the value of r. So from if we know tau zero, then we can say that r is equals c tau zero over 2. So what are the observations of this procedure? So we receive a echo, echo is received, but first of all we transmit a pulse. So a pulse is transmitted, which is shown here. So we transmit a pulse from the antenna, and then after tau zero time, which is shown here, after tau zero time, we receive the waveform which is plotted here. So uh, uh, the received echo is decreased in amplitude. So this might be the typical value might be 5 volt plus minus 5 volt here, but the received waveform will have a very small amplitude, say 0.00002 volt. So this received echo is decreased in amplitude due to propagation loss. So it propagates, so there is propagation loss, and this may be also buried in the background noise. So there are a lot of background noise. So apart from that, a typical delay is also introduced by the radar processing system. So we get a delay tau zero plus some additional tau prime, which is the delay from the radar processing system. So the received waveform, then this received waveform is sampled. Okay, so it is passed to a analog to digital converter. So if we have a received waveform like this, then they are sampled in time. Okay, so they are sampled in time, and we receive these samples. So these samples are then processed inside the radar processing system. So this is how we process the samples, and then we estimate tau zero, and then we get the estimate of R, which gives an idea of the range of the aircraft. So in sonar, uh, the objective is to determine the position of the target. So we have a target here, and we want to determine its position. Okay, so we want to determine so it out here, and we want to find its position. So how to do that? So we have a ship here, and an array of sensors is connected to this ship here. So the objective is to determine the position of the enemy target, such as submarines. So how to do that? So first of all, note that this target radiates lot of noise. So lot of noise is coming from this target, which might be created from the machinery or the propellers. So this noise is actually the signal of interest. So this noise propagates through the water, and then it is received by the sonar array. So the output of this sonar array is then fed to the digital computer here. Okay, so let's suppose that there are three sensors on this array. So this is the output of sensor 1, this is the output of sensor 2, and this is the output of sensor 3. So we observe that the signals received by the sensor 1 and the signal received by the sensor 2, there is a slight delay. So which I'm showing here. So so this is the starting point of the signal for sensor 1, and this is the starting point for the signal of sensor 2, and then there is an additional delay in the signal of sensor 3. So we see that the signals are received at the sensors with a slight delay. So we call that delay as tau zero. So this delay here, the delay tau zero in received signal is to be measured. Once this delay is measured, then we can get the bearing of the target, that is beta. So this beta equals cos inverse C tau zero over D. So what is D here? So D is the separation, it's the distance between the sensor. Okay, so we already know the distance between the sensor, and we measure the delay, then we can get the bearing of the target. But since the received waveforms, so these waveforms are not clean. Okay, so these waveforms which are shown here are not clean. They might be noisy. Okay, so they might be noisy here. They might be buried in some kind of noise, like these signals might be buried in noise. So we will get a noisy estimate beta. So this estimate is also noisy. So in the next example, we are going to discuss about the speech or estimation theory is used in speech processing. So one of the fundamental tasks in speech processing is speech recognition. Speech recognition. That is, we recognize each speech sound or phonemes, for example, vowels and consonant. So user will speak some vowel or consonant, and then the machine will recognize which vowel or consonant has been spoken. So how to do it? So one method is to we store three waveforms. Okay, so here is shown a waveform, a typical waveform for vowel A, and this one is the typical waveform for vowel E. So we can store three samples of these waveforms for a person. So a person speaks A, and then we ask him to repeat it three times, and then we say the waveform. Then the person speaks E, and then he repeats it three times, and then we say the three waveforms. After that, we ask the person to speak A or E. Okay, so the person will either speak A or E, and then we compare the spoken vowel with each waveform. So with each waveform, and some form of distance measure can be used. But the problem is that the pitch might change, resulting in the change of the waveform. So other properties like spectral envelope, which doesn't change with pitch can be used. So to model the speech, so the method is to model the speech, that is this is speech and this is speech as a linear predictive coding. So we model the speech as a linear predictive coding, and then And then we estimate the modern risk is linear predictive coding, and then we estimate the parameters. Okay, so we estimate the parameters of this linear predictive coding, which is an estimate of the spectral envelope. So here an spectral envelope is shown for the model A. So this one is the paritogram, that is the spectral envelope, the black one, and the dotted one is the linear predictive coded spectrum, that is the estimated spectrum. So if we can estimate the spectrum approximately, then we can say we can recognize whether the vowel A or vowel E was spoken, because if we see that the spectral envelope, that is the spectral envelope for vowel A and for vowel E are different. So then if we can estimate the spectrum, the LPC spectrum of vowel A and vowel E, which doesn't vary with pitch, then we can estimate better whether which vowel was spoken. So in a particular estimation problem, we have a continuous signal. Okay, so we have a continuous signal, and then this signal is passed through a sampling process, which gives discrete time samples. So these are discrete time samples, and then these samples are passed through a digital processor, and then we get an estimate of our parameter theta, which might be tau zero or beta or LPC spectrum. So instead of the continuous time signal, we have the samples. Okay, so we have endpoint data set, that is x0, x1. So we have endpoint data set x0, x1, xn minus 1. So so these data sets depend on the unknown parameter. Okay, so these data sets depend on the unknown parameter, which we call theta. So theta is a function of these data sets, that is x0, x1, dot 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 xn minus 1. So in a typical estimation problem, we need to determine the function g. That is, what is the function g, which will give an estimate of the unknown parameter theta. So in today's lecture, we have introduced the applications of estimation theory. In particular, we have discussed about radar, sonar, and speech. Thank you.